this video, I'm going to talk about the different types of circuits, and really I want to make sure you understand what's different or similar between series and parallel circuits. We start with just what I call a simple circuit. In a simple circuit, we generally think of having some type of battery or power supply, and then something that's using that power. Simplest one that I can think of, and this would absolutely have only one path, would be made up of a light bulb. There's our connections. And a battery. And as long as that path's closed, our battery is going to light. We generally think of charge flowing out of the positive terminal into the negative terminal. There's our current. That's a simple circuit. It can't get any simpler than that. In a series circuit, we maintain the one path. But when we do it, we can add more than one thing. So for example, we might have 2 light bulbs. And still, let's have our battery down here. Here's our battery. So current leaves here, it goes into the first one, goes through that light bulb. We can even draw it going through if we wanted to. And then connect that one to that one. Current again goes through the second one. And then comes all the way back around. That current flows in exactly one path. Okay? What we notice when we do this, if we put in 2 resistors in parallel, we actually just doubled our resistance. It's twice as hard for that current to flow. And since it's hard for current to flow, our light bulbs are still going to glow, but they'll be less bright. Notice I put like 8 little glow marks here, and I put 4. So they're going to be less bright. So one of the disadvantages when we keep putting things in series is we have less energy basically for each of the items. If this is, let's just say it's a 9-volt battery. Well, if it's a 9-volt battery here, this is getting all 9 volts, or all 9 joules per coulomb. This is only going to get 4.5 each, half of 9, so it's not going to glow as bright. If we were to put a third one in, there's 1, 2, 3, connect them all together, connect, connect, connect. There's our battery, minus, plus. It'll glow, but it won't be as bright at all. In fact, if we did this in the lab, which we normally would, by this point, it's really dim. And again, if we had 9 volts, well, here, this is getting 9 volts. Here, these are each getting only 3 volts, or only 3. So it's very, very dim. Okay. One of the problems, too, with a simple circuit is in order for current to flow, you have to have a continuous path. If I take this light bulb out and I unscrew it, this one goes out because that stops the path of current. It's like breaking it right there. Or if one of these light bulbs burns out, if this one burns out, well, when the light bulb burns out, that filament literally burns in 2. It breaks the current. So we don't have a continuous path. So one of the disadvantages with a series circuit is that if one thing goes out, everything goes out. Okay. One of the things that's kind of nice about a series circuit that I want to make sure you understand is when you have a series circuit, the current is the same everywhere. going to have more current. Let's suppose each of these light bulbs is 3 ohms of resistance. We're just making numbers up. So if I have 3 ohms here and this is 9 volts, then I'm going to get 3 amps of current because 9 divided by 3 is 3 amps. But here, if this is 9 volts, and let's say I have both bulbs in here and they're both still working, well, that's 6 ohms. Well, 9 divided by 6 is only going to be 1.5 amps. I just cut my current in half because I put twice as much. Here, if they're each 3 and they're all working, nothing's burned out, I'd have 9 ohms of resistance and 9 ohms, I'd be down to 1 amp. So I went from 3 amps to 1.5 amps, down to only 1 amp. So they glow less each time. Okay, but in a circuit, if this, let's just say that this has 1.5 amps, that means 1.5 amps flows to the battery, 1.5 amps flows to the first bulb, 1.5 amps flows to the second bulb. There's only one current path. So whatever current is flowing, it's the same in each and every part of the circuit in a series circuit. Okay. You can have different amounts of voltage. You can have a small voltage bulb and a big voltage bulb, but you're going to have the same current in each part of a series circuit. And it makes sense that every time we introduce a new resistor, we put something else in that circuit that increases the resistance, which means there's less current for each thing to use everywhere, okay? Like I say, and one of the real drawbacks is the old-timey Christmas lights a long, long time ago, if one bulb went out, they all went out. And this is why they were wired like this. And as soon as this one went out, we broke that current path and the whole circuit went out, okay? Because of these drawbacks, we don't have our houses and homes, they're not wired in series. Series is easy to understand, but it's not practical. If every time we plugged in an appliance, everything else got a little bit less current, that wouldn't be good. Or if every time we turned something off or something broke, the whole circuit went out, that wouldn't be good. When you wire in series, everything would have to be on like all the time. Okay. So how do we do it? What's the other option? The other option is to wire things in parallel. In parallel, there's more than one current path. In parallel circuits, there's more than one current path. And if you think about it, each new path allows more current Before I actually draw a picture of a parallel circuit, I want to explain, why does each new path mean more current's going to flow? Well, let's suppose that you had a water tower. So it's sitting up here, you're out on a farm, you like Petticoat Junction, you got a big old basin full of water standing up on stilts. You probably never saw the TV show Petticoat Junction, but there it is. It's full of water. Your barn catches on fire. Well, you've got a little spigot up here and you go and you catch your toes and water starts flowing. Why does the water start flowing? Because of gravity. That's why they put those water towers up there high so the water can flow. So here's the water flowing, water, water, water. Here's a fire you're trying to put out. Fire, 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 right? Your neighbor says, hey, I have a water hose. You want me to help? Are you going to tell him yes or no? You're going to tell him yes. Because you know if he has a water hose, whether he has a water hose that's bigger than yours, you got a pretty big water hose, or whether he has a water hose that's smaller, it doesn't matter. More water is going to flow. If he can come up here and hook up here with his little water hose, now we got even more water flowing to put out the fire. In fact, if we had a whole bunch of neighbors and we had a whole bunch of spigots we could tie into, we could drain that a whole lot faster. Now, one of the disadvantages with having a lot of stuff in parallel with a battery is you might drain your battery really fast, because this is like the battery. It provides the water pressure, it's gravitational, to keep that water flowing. But every time you add a water hose, whether it's a big hose or a little hose, more water is going to flow. So you reduce the overall resistance. More water flowing is less overall resistance to flow. Okay, what's that look like with wires? With wires, it looks like this. Here's a light bulb, and here's a light bulb. And here's a battery. This light bulb's connected right here, and so it glows nice and bright. You go, okay, if I go ahead and I connect another light bulb right here, and I can do it by connecting it all the way back to the battery, or I can just actually tie in someplace like right here, that's still connected. You know what? That one's going to glow, and it's going to go just as bright as the other. It's really like having those two separate water lines. How bright they glow are going to depend on this resistance and this battery. So, if this is 9 volts, and this is 3 ohms, and this one's also 3 ohms, you know what's going to happen? 9 divided by 3 is 3 amps of current flowing through this one, and 9 divided by 3 is 3 amps. It's going to have 6 amps flowing through it. It's not going to have the same current everywhere necessarily, because if it's connected like this, you're going to have 6 amps, and right here at this junction, 3 amps will go that way, and 3 amps will go that way. The current will actually divide. There's more than one current path. Now, this has a lot of positives. For one thing, if this one goes out, that one doesn't get affected at all. It doesn't get brighter, it doesn't get dimmer, it doesn't go out. Okay? If I unscrew that one, same thing. So in a way, when they're in parallel, it's kind of like they're all their own little circuit, but they just happen to be sharing that particular power supply or that particular battery. Now, if I add a third branch, I can add the third one. I add the third one. I'll have to erase this because I want to add it up above. Well, again, if it's got the same light bulb that draws 3 amps, well, now that if this one's drawing 3 amps, and this is drawing 3 amps, and this is drawing 3 amps, now the battery's supplying 9 amps. So one of the disadvantages is it's going to drain that battery quicker if we're relying on batteries. The other disadvantage is if this number gets too big, this wire can get too hot and overheat. Okay? So we have to think about safety a little bit. Our homes are wired in parallel. Okay? You have multiple parallel circuits through your house, and each circuit's going to have its own either fuse, if you happen to live in a really old house, or more likely a circuit breaker. Basically, a circuit breaker is a switch that opens up and stops the current anytime the current gets too high. A household circuit typically would have maybe a 10 amp or a 15 amp fuse in it or circuit breaker. because household wiring for those wires is probably designed to be safe as long as currents stay below 15 amps or so. Okay. Some of your larger appliances, maybe your air conditioning units, or if you have an electric stove, those may be wired for, say, on a 30 amp circuit breaker, because those will draw more current safely. They're going to use heavier gauge wire and things to accommodate that. Okay. Let's look at some combinations. If we think about it, we can figure out what's going on. Suppose we had a situation with 3 light bulbs. These 2 light bulbs are wired up in parallel. They're connected one to the other. But a 3rd light bulb is connected in series. Now, what we really have to think about, if all of these bulbs are identical, let's think about what would happen and which would glow brighter. I haven't really necessarily drawn the glowy part correct. We know that charge is going to leave here. And it looks like all of the charge has to flow through this particular one. So if this is 3 amps, then 3 amps is flowing. So this is going to get all the current. But notice when it reaches here, the current splits. Half of the current's going to go through the upper bulb and half of the current's going to go through the lower one. These are not going to be as bright because that current had to split. So it's not quite so bright. Now, that makes sense to everybody. If you have all the current flowing through the first bulb, the way I've drawn it, but that current splits in half, half goes through here, half goes through here, won't go quite as back. They'll get to here and that current will all come out again, and all of that current will go back into the battery. So however much current there is, if 3 amps is here, 3 amps through here, all of a sudden it splits in half, 1 1/2, 1 1/2, but back together. Now, if this light bulb goes out, the whole circuit stops because it breaks the whole circuit. But if this one goes out, oh, well now it's just a plain old series circuit. It'll all go through here. These 2 will now be equally bright because now all of the current will be going through that one. It'll just be a series circuit now. So you kind of have to pay attention to think about what's going on. Let's draw a slightly different pattern. There's a light bulb. There's a light bulb. Here's a light bulb. Here's the battery. This is a type of parallel. It's a combination circuit. Notice that one path goes to the bottom and one path goes to the top. Now, if these are identical bulbs, and this is, say, a 6-volt battery, this is going to get all 6 volts. These are only going to have to share. So when we look at how these are going to perform, we can see it makes sense if this light bulb would be really bright, and these not quite so bright. Okay? Now, if this bulb burns out, we still have a complete path and the top 2 bulbs will continue to light up. If this one burns out, the bottom path is complete, it won't be changed, but both of these bulbs will go out. because you've broken that top loop. So when you're trying to answer those questions, look and see which loops are still continuous and which loops are not. Now, I can make the whole thing go out by drawing a short circuit right here. If I take a little piece of wire right here, well, that's the easiest path of all, so none of them will light up. There's no reason for current to flow up through this top path, which has 2 resistors. There's no reason for current to flow through this path, which has this light bulb, if it can flow right through the wire and avoid all of that. That would actually make all 3 of them short out, okay? Now, see if there's anything else I need to remind us about. I guess the last thing I just want to review, we've talked about these ideas, is that in the United States, our household circuits are 120 volt. They're 60 hertz alternating current. We haven't really talked about alternating current. Batteries use direct current so that the charge is always flowing in one direction. And alternating current, charge flows in one direction and then reverses, and then reverses, and then reverses. In fact, 60 hertz means it reverses 60 times every second. It doesn't change how we do our formulas. It doesn't change Ohm's law or anything like that. So households run on about 120 volt outlets, and the circuit breakers are there primarily as safety, since they are wired in parallel, that if we plug too many things, that the wiring doesn't overheat and start on fires. I think that's it. Good luck. If you have questions about the homework, certainly you might email me about those. We only have one more chapter left in this text that we're going to do. That's chapter 22 on electromagnetism.